Well, good afternoon slash good morning slash hello, wherever you folks are. And welcome to another edition of Takeo Tuesday. My name's John Barba, and I'm joined with my good friends and compatriots, Rick Mayo and Dave Holdorf. Together, we comprise 60% of the Takeo training squadron. Those of you who are regular Takeo Tuesday guys know Rich Medeiros and Brett Zerba, who handle our commercially focused training. And Rick, Dave, and I take care of the residentially focused training. So we're happy to have you with us. We're psyched. We've got a pretty cool presentation for you today called Flow, Head, and Sizing Considerations for ECM Circulators. And this one's kind of near and dear to all of our hearts here at Takeo, and it's important, I think, for everyone to really fully understand, because even though ECM variable speed circulators have been with us for a while, people still think they're magic. People still don't understand that we're talking about system curves, we're talking about pump curves, we're talking about control curves. The fundamentals of circulator selection still apply, even though these things can in fact vary their speed or have different performance ranges beyond just a normal fixed speed or even a 3-speed circulator. They can do interesting things, but they don't size themselves. They're not magic. They're not anything like that. The person doing the installing, the guy who takes that thing out of the box and sticks it on a system, really has to understand what these things can do, what they can't do, and how to utilize these marvelous little pieces of technology to get the very most out of their heating system. We've said it many times before that the circulator has more to say about overall system-wide efficiency and economy of operation than we've ever given it credit for. And that is largely due to the performance characteristics we can get out of these variable speed circulators. They really make fine tuning and maximizing the performance of a system possible. And that's why it's so important, so critically important, that you guys know exactly what they do and, more importantly, what they don't do.
Yeah.
Now, before we get started, I just want to share with you a couple of the rules of the road. First and foremost, just to make sure that I haven't been talking to myself for this entire time, on your control panel, you should see a little area to ask questions. It's on your control panel, and if you could do this for me, just type in a hi, hello, how are you, so I know that you know
They're
that
coming
you,
in.
A, how to do this, and B, that you can hear me, and I'm seeing a whole bunch of them pop up, so that's good
Yeah,
news.
very good.
There we go. Now, Rick and Dave will be monitoring your questions, and we're going to be stopping every few slides to answer your questions. So I encourage you all to ask questions as they occur to you. One thing we don't do at Takeo is we don't tell, hold all your questions till the very end. And that to me, that says we don't want to hear from you till we're done talking. These things work best when they're collaborative, when they're almost conversational. So if you have a question, when it pops up, just let us know, okay? And type it in, and we'll answer them as we go along. And we'll stay on, a little bit afterwards if you have any additional questions. That's certainly not a problem. The other thing I would encourage y'all to do is treat this like you would treat an in-person classroom training. And what do I mean by that? I mean, get yourself a pen and a pad of paper and take notes, just like you would in a real class, okay? A lot of people say, well, I'm taking notes, I might miss something. Well, no, not really. Taking notes actually is a powerful tool to help you stay focused and to pay attention to the program. With webinars, it's really easy to get lost. All right, oh wait, my phone just rang. Oh my God, I got a text, I got an email, I better check that out. Oh, what's going on Facebook? You can get lost a little bit. So what will help you guys the most and help you get the most out of the next hour? Focus on taking notes, paying attention. You will get a link tomorrow to a recording of this class. So that's all taken care of. You're going to get that automatically. So you can go back and watch it as many times as you want. And that's cool. So you'll have that at your disposal. But just get the most out of this class. Hang in there, take some notes, and ask some questions, and everything will be happy. So are we ready out there, gang? Any interesting questions so far? Are we any comments out there that we got to address before we get started, guys?
No, I had somebody having issues. I'm going to have them sign off and sign back in. So.
Yeah, if the audio's choppy, that might be something you might have to do.
He said he couldn't hear anything, but
or
Yeah.
And there's check your audio settings also on your control panel. That might help as well. Which telling someone who can't hear to check his audio settings on his control
Nah.
panel is kind of a
Yeah.
waste of time.
I
But
did type something to him. So
there you go. Okay, good. Well, let's get started here then. With variable speed ECM circulators, it all starts exactly the same place as it would start with any circulator, a fixed speed circulator. It starts with flow and head. You really need to know the flow rate that you need for the application required, as well as the head loss or the head pressure loss for said application. So we need to know the flow rate and we need to know the head so we can fine tune these circulators, because they don't fine tune themselves. That's very important to understand. I don't care how many buttons you push, they do not fine tune themselves. So we need to calculate flow and calculate head. We can't separate that from circulator selection. It doesn't matter what kind of an ECM circulator you use. The thing about flow and head is they kind of go together. If flow goes up, head goes up exponentially, or head pressure loss within a piping system, it goes up exponentially. So the more you pump through a system, the more pressure loss there is. What we're trying to do is we're trying to find the right flow and overcome the head loss that is there. We don't want to overpump. And again, that's another element of circulator selection. Yes, we want to deliver the flow and overcome the head loss, but we don't want to overdo it. If we overpump, we start to create a situation where the delta T in the system gets smaller and smaller and smaller, even though it's quite cold outside, and that causes short cycling, which kills efficiency and shortens the lives of components. So we want to make sure we get that part right. And figuring flow is pretty straightforward. We use this formula right here. That is what we call the universal hydronics formula. And the universal hydronics formula states that GPM equals BTUH divided by, and let's make this a little more technical, divided by the product of delta T times 500. Now let's identify these terms. GPM, of course, is gallons per minute. That's the flow rate you need to deliver the BTUs required. BTUH, of course, that's the BTUs required at any given point in time. When we're sizing a circulator, when we're sizing pipe, when we're sizing a boiler, the BTUH is generally speaking the load of the zone or of the system under design conditions, that quote unquote coldest day of the year. We always design for that worst case scenario. Delta T is the designed for temperature drop of the fluid as it goes through the system. That's the design for temperature drop. With our design for temperature drop, what we're talking about is typically speaking, in most residential hydronics, we're talking about a 20-degree delta T, a delta T of 20 degrees, meaning maybe the water goes out at 180 and it comes back at 160. All right, that's a 20-degree delta T for an average water temperature of 170. For for a lower temperature system with a ModCon boiler, maybe that water's going out at 130 and coming back at 110 under design conditions. That's what we're gunning for, and that would be an average water temperature of 120. There are some exceptions to that rule. Residential radiant floor heating is often designed around a delta T of 10. So the water might go out at 120 and come back at 110 for an average of 115. That's done for the consistency of floor surface temperature. So you have warmer spots and then less warm spots, so to speak. Indirect water heaters might be designed around a delta T of 30, meaning maybe the water's going out there at 190 and coming back at 160 perhaps. And then with ModCon boilers, you can pick your delta T across that heat exchanger, which is basically, that's a different webinar. But that's the delta T. And for our purposes today, we're going to presume normal residential hydronics, and we're going to look at a delta T of 20 degrees through our system, our jobs today. 500 is a mathematical constant. 500 comes from multiplying the weight of 1 gallon of water, which is 8.33 pounds, times the number of minutes in an hour, that is traditionally 60, times the specific gravity of the fluid. 100% water has a specific gravity of 1, times the specific heat of the fluid. 100% water has a specific heat of 1. 8.33 times 60 times 1 is 499.8. We'll call it 500. Now that 500 is at room temperature. Obviously, we're dealing when the water temperature goes up, The density of the fluid goes down, specific gravity changes, things like that, they all change. You might find at 180 degrees, we might be looking at a 490 number. If you add glycol to the system, that changes as well because the specific heat is different. So a 70% water, 30% glycol solution might drop that number down to say 475. So you've got it, that just simply requires math. For our purposes today, we're going to work with 500, just again to keep things simple. So GPM equals BTUH divided by the product of delta T times 500. Now let's say I'm doing just a simple single zone of radiation. Could be cast iron radiators, could be baseboard, could be cast iron, whatever. It's simple residential hydronics at a 30,000 BTU load. So the load of that zone under design conditions is 30,000 BTUs. To find the flow, I'm going to divide 30,000 by the product of 20 times 500. Again, we'll put the parentheses there. 20 times 500 is 10,000. So 30,000 divided by 10,000, I'm going to need a required flow rate of 3 gallons per minute for that one zone, okay? 3 gallons per minute for that one single zone. So far, so good. That's half of the equation. Now we got to find the head loss. Now, calculating head loss, there's a lot of ways to do it. There's some simplified versions, and what we're going to show you is kind of a combination of the two. It's a simplified version plus, doing a little bit of math to get the head loss right for the specific flow rate. So head loss is basically friction loss. As the water goes through the pipe, it's rubbing up against the sides of the pipe, it's hitting fittings and changing direction and things like that. And that's causing pressure loss due to friction as the water goes through the system. Now we talk about head in feet of head, and too often people think feet of head equals feet of height. I got to pump that water up 3 flights of stairs, so it's got to go up to the 3rd floor. I got to figure the lift. No, you don't. It's a closed loop system. It's a closed loop system like so. So think of a Ferris wheel, okay? If you're sitting on this cart on the Ferris wheel, does the motor on the Ferris wheel have to lift you up? No, because there's some other guy in the cart over here coming back down, all right? So the weight of the water is kind of like a counterbalance. I don't have to lift the water up to the 3rd floor. It's already there. We've already filled and pressurized the system. All the circulator has to do is quite literally circulate the water. We call them pumps, but really they're circulators. So when you're talking about friction loss, all we care about is the length of the run, okay? And the length of the run is from the Gazauta side of the circulator all the way around back to the Gazinda side of the circulator. Now, new construction, maybe, or you can measure it and figure it out. If you're doing a boiler replacement or something like that, the best you can do is estimate, all right? The best you can do is estimate. So you measure that length as best you can, and then to allow for valves and fittings and stuff, you simply multiply by 1.5. You multiply by 1.5. We're adding 50% to that length to allow for valves and fittings and stuff that's in the way. For example, a 3/4 inch copper elbow has the same pressure drop as 2.5 feet of straight copper pipe. All right, so we got to allow for that. A 45 has the same pressure drop as 1 foot of pipe. A T has the same pressure drop as 5 foot of pipe, and so on and so forth. So rather than counting them all, which we can't do, we're simply going to allow for that by multiplying by 1.5, add 50% to that length to allow for fittings. Once we have that number, then we can figure out what we call our total developed length. So we measure the length. In this case, I'm using 163 feet, multiplying it by 1.5 for those fittings, and I come up with approximately 245 feet worth of total developed length. So that's how much, if I flattened out all those fittings and made it one big old long run, we're talking 245 feet. So 163 times 1.5 equals 245. Now, what do we do with that number? Well, we're going to take a look at this here chart, which comes from the Copper Development Association's Copper Tube Handbook. And the Copper Tube Handbook is one of those books that if you are really into copper and you want to know everything there is to know about the molecular structure of copper, how it's annealed, how it's mined, what the guy who mined it had for breakfast, all that crazy stuff, this is a great book to read. If otherwise, you just want to look at Table 6. Now, Table 6 is a pressure loss chart. It gives us the pressure loss of water due to friction, which is what we've been talking about, in types K, L, and M copper tube. And what it does is it breaks it down by flow rate. It breaks it down by specific flow. Because again, we said earlier, as flow goes up, head loss goes up exponentially. So when you're calculating your head loss, you want to try and calculate it to as close as the actual flow rate that you need as possible so you don't overdo it. Now, what this is doing is it's giving us our pressure loss in PSI per linear foot. I'm going to show you how to convert that to feet ahead in a second. Now, with 3 gallons per minute, we're going to be using 3/4 inch type M copper. All right, our pipe sizing guidelines tell us if my flow rate is 2 to 4 GPM, I'm looking at 3/4 inch copper. 4.1 to 9 GPM, I'm looking at 1 inch copper. 9.1 to 14 GPM, 1.25 inch copper, and 14.1 to 22 gallons per minute is 1.5 inch copper. That's based on minimum and maximum fluid velocities, a minimum velocity of 2 feet per second, a maximum of 4 feet per second. Can we cram 22 gallons a minute through 3/4 inch type M copper? Give me a pump big enough. We sure as heck can do it, but we're going to be well in excess of that 4 feet per second velocity guideline. We're going to have a noisy system. It's going to be noisy like crazy. In addition, it's going to be, we're going to erode the pipe from the inside out. So we want to stay within those guidelines. Now, with 3 gallons per minute at 3/4 inch M. So I go here for my 3/4 inch M. Here's my 3 gallons per minute, and I follow the row and the column to where they intersect, and I'm going to intersect at 0.009 PSI per foot of pipe. So that's for 1 foot of pipe, 0.009 PSI per foot of pipe. All right. Now, what am I going to do with that? Well, I've got 245 feet of equivalent length, right? So I'm going to multiply 0.009 PSI per foot of pipe times my total feet of pipe, which is 245 feet. And that will give me the pressure loss, the PSI pressure loss at 3 gallons a minute through that circuit. And that's going to come out to 2.2 gallons per minute. So if I had gauges on the Gazinta and Gazzouta side here, and I was pumping at 3 gallons a minute, the Gazzouta gauge would read one number, the Gazinta gauge would read 2.2 PSI lower. All right, that's kind of how that works. Now, how does PSI convert into feet ahead? Well, it's pretty simple. PSI converts to feet ahead, dating back to, if anybody out there has a plumbing license, you might have learned this in day 1 of plumbing school. In day 1 of plumbing school, we learned that a column of water 28 inches high will have a gauge pressure at the bottom of 1 PSI. It'll have a gauge pressure at the bottom of 1 PSI. Now, another way of saying 28 inches is 2.31 feet. 2.31 feet of head. All right, 2.31 feet of head per PSI. So to figure out what we need here, we're going to multiply 2.2 PSI times 2.31 feet of head per PSI. All right, per PSI. So there we go. I think we're back now. 2.21 feet of head per PSI. And multiply that out, and we're going to have 5 feet of head. So 2.2 PSI times 2.31 feet of head per PSI. That gives us 5 feet of head loss. So our circulator for this particular system is going to need to be give us 3 gallons a minute at 5 feet ahead. How are we doing out there, guys? Any good questions or anything we need to know?
Mostly just folks wanting to know about PEX because we're showing just copper right now, but just remind them that the PEX people have similar charts.
There we go. Okay, now I can hear you.
Yeah. Can you hear me now?
I can hear you now. Yeah, my headphones went dead, so I had to change them on the fly.
Ooh, you were fast.
Hey,
mostly, John, just checking on PEX because a lot of people using PEX in lieu of copper. So Dave and I have both just said, hey, check with your PEX manufacturer. They'll give you similar charts to this, and you might even have a slide that's going to talk about PEX. I don't know.
I don't have one in this presentation, but before we part, I can dig it up. With PEX tubing, the manufacturers have their own pressure loss charts, and they'll either give you feet of head per foot of pipe, or in some cases, they'll give you feet of head per 100 feet of pipe, and you have to kind of math that out. They generally don't give it to you in PSI. They will give it to you in feet of head. You'll find that a 3/4 inch PEX, 3/4 inch copper, you're actually going to have more pressure loss per foot with 3/4 inch PEX than you will with 3/4 inch copper, simply because the wall is thicker and the ID is smaller. The difference may come in the fact that you're not going to have nearly as many fittings, or you shouldn't anyway, with PEX as you would with copper. Again, it depends on what you wind up using, but more often than not, you'll have the head loss might wind up being reasonably close, depending upon how many fittings you use with your PEX. So good?
Good.
So 3 gallons a minute at 5 feet ahead. Now that we have that information, I want to throw a nice little curveball at you. We're going to talk about system curves. Pump curves we come up with at the factory. We have a big rig that'll figure out what the pump performance curve is at different flow rates. We have a horsepower, we have a motor of a certain horsepower, and we have impellers of certain designs that will create specific pump curves. It could be a high flow, low head, flat curve type of pump curve, or it could be a lower flow, higher head, steeper curve type of pump curve. That we come up with at the factory, and by comparing pump performance curve charts, you'll be able to see what you're looking at. The thing that we want to focus on now is the system curve. You don't need to know how to figure out system curves unless you really want to. The important point about a system curve, the most important thing about a system curve is A, you know they exist, all right? And B, you need to know the shape. It's not a straight line. As flow goes up, head goes up exponentially. It's one of the first things we talked about. And that's reflected by a system curve. The reason the system curve is important is this, let's say I need to work right down here. Let's say that, okay, whatever gallons per minute this is, let's say it's 5 gallons a minute at 5 feet ahead. Let's say this is my requirement for a specific zone of heat. This is where I want it to work, but I'm slapping this particular pump on that job, all right? Once I do that, physics takes over. Energy in equals energy out. When you put a pump on a system, the system has to work somewhere on that pump performance curve. It has to. So it's not going to work here. We just did a lot of math to figure out where we wanted it to work, but it's never going to work there. Once I put this circulator on, the system's going to work right here at whatever head. Let's say that's now 10 gallons per minute at 11 feet ahead. So what I've done here is I've basically doubled the flow to the zone, or to the unit heater, or to whatever it is I'm trying to deliver BTUs at. I've doubled the flow rate than what it needs under design conditions. So it's not that I'm going to get more BTUs out of it. I'm only going to get the BTUs out of it that I'm going to that it needs. But what I've done is, if we remember, GPM equals BTUH divided by delta T times 500, right? Then if you can read that, you're better than I am. 20 times 500, right? And let's say this was 50,000 BTUs, and I needed 5 GPM, right? Well, I'm not giving it 5, I'm giving it 10. I still need 50,000 BTUs, but what's going to give? My delta T is going to give. I'm not going to have a 20-degree delta T. The best I'm ever going to see here is a 10-degree delta T, and I've just kicked short cycling into overdrive. All right, that's the danger of over pumping. All right, and that's why it's important to know that system curves do in fact exist. Because again, I do a lot of work to figure this out. I just slap out whatever my favorite pump is on there, let it go. I'm over pumping, and I'm limiting the efficiency and economy of operation of the system. Let me know if that makes sense to you, because this is so common out there in hydronics. It's so common. And the thing about it is, guys will say, well, I've been doing it this way forever and I've never had a problem. So I don't know what you're talking about. Well, we have to identify problem. We have to define what we mean by problem. If you define problem as, well, the system doesn't work, we're not delivering heat, people are mad, they're freezing to death and blaming me. Well, no, you don't have a problem. You absolutely don't have a problem. Are you going to be able to deliver 50,000 BTUs as needed with 10 gallons per minute? Well, yeah, you can do that all day long and twice on Sunday. That's not the problem. The problem is we are deliberately short cycling the boiler, which means whether it's a cast iron boiler or a mod con boiler, it's never going to be as efficient as it could or should be, ever. number one. And number two, when we start doing the short cycling thing, we're turning things on and off and on and off and on and off like that. Well, what do you think is going to happen to all of the moving parts? We're going to start wearing things out prematurely, and we're going to have premature, unexpected, and unwanted service calls to replace potentially fairly expensive pieces of equipment. Now, that to me sounds like a problem. All right. But there's never an immediate problem like, oh, the system doesn't work, they're freezing to death, they're blaming me. Goodness. No, it's a much longer term problem and potentially much more insidious. All right. So that right here is a perfect picture of over pumping. So there's a math formula for plotting the system curve. Okay. I know 5 gallons a minute at 5 feet ahead in this example. I know the head flow and head requirements that I have. What I can use those numbers to figure out the different points on my system curve plot so I can figure out where my intersection point is. Now, you may never do this math because this math is here. I'll show you the math way, and then I'll show you an easy way. The math way is this. Head 1 divided by head 2 equals flow 1 divided by flow 2. Now, you know head 1 and you know flow 1. We know these two things. We just figured them out. In our example from early on, flow 1 was 3 gallons a minute. Head 1 was 5 foot ahead. Okay. Now, the way you would use this formula is you'd simply choose flow 2. I want to figure, I know the head at 3 gallons a minute. What would the head be at, let's say, 6 gallons a minute? All right. You pick what you want for flow 2, and then using algebra, you determine what you want, what head 2 would be. So let's take a look. So 3 gallons a minute at, I'm sorry, that should be 5 feet ahead. 3 gallons a minute at 5 feet ahead is what we had determined. Okay. So head 1, 5 feet divided by X, because that's what we're trying to find, head 2, equals 3 gallons a minute divided by 6 gallons a minute, because I want to figure out what the head is at 6 gallons a minute squared. So 5 divided by X equals 3 divided by 6 squared. All right, let's just continue to math that out. 5 divided by X is 3 divided by 6 is 0.5, right? 3 divided by 6 is 0.5. So 5 divided by X equals 0.5 squared. Math that out. 5 divided by X equals 0.25. All right. We continue to math that out, divide both sides or multiply both sides by X to start to isolate for X. Multiply both sides by X. 5 equals 0.25X. Now we divide both sides by 0.25 and we come up with 20. So here you can see we doubled the flow, we quadrupled the head. So it goes up exponentially. By doubling the flow rate, we quadrupled the head loss through the piping system. So now I have, if I'm thinking about a chart, I've got 3 gallons a minute at 5 feet ahead, and now I have 5 gallons a minute at 20 feet ahead. And using this math formula, I can figure out 1 gallon a minute, 2 gallons a minute, 4, 5, 6, 7, however many I want to figure out. That's the math way to figure out the different points that you would put on that plot when you're laying out a system curve. The easier way is to use something that Bell and Gossett developed, and kudos to them. And this was Gil Carlson, the grandfather of modern hydronics. He developed this way back in the late 50s, early 60s. And this is the Bell and Gossett system sizer wheel. Scale number 5 basically does all that math for you. And scale number 5 on the back side of the system sizer wheel, up top here you have feet ahead, and in this white window right here, you have your flow rate. That's your GPM. Now, the way you would use this is you would line up 3 gallons a minute with 5 feet ahead, known flow, known head. Now to figure out the rest of your head loss, you simply, okay, go back here. Let's look at 2 gallons a minute. 2 gallons a minute, I'm at roughly 2.3 feet ahead. 3 gallons a minute, or 4 gallons a minute, I'm at 9 feet ahead. 5 gallons a minute, I'm at 14 feet ahead. 6 gallons a minute, I'm at 20 feet ahead. 7 gallons a minute, I'm at, looks like 28 feet ahead. Okay, so what Gil was able to do here is set this thing up in such a way that it does the math for you in a wheel basis. So let me know if that makes sense to you, but that's another way, an easier way to plot out a system curve if you wanted to. And that's simply using scale number 5 on the B&G system sizer wheel. All right, any questions out there, guys, that we want to address, or how are we poking along?
Poking along good. The people are having issues with losing the voice, and we're just telling them to log off and back in. I think that's working okay.
Okay, all right. Is it? I know I was having some internet issues earlier today, and I was hoping they were getting solved. So,
Todd wants to know if these system sizers are available. What are you going to tell them, John?
well, not from us, obviously. We don't. They're not one of our products. There's various software out there that can help you do this math. System sizer wheel it's not a Takeo product, so we don't have them available to give out. There are various apps and things you can download that can figure this out for you. And again, showed you the math earlier. Yeah, as far as the easy way, you'd have to get your hands on a system sizer wheel to be able to do this, if that helps. Zorite. And let's continue. So here's, if we just look at our sizer wheel, here we have the different head losses at different flow rates. So at 1 gallon a minute, we're at 0.6, 2 at 2.3, et cetera, et cetera. So now I have all of these different points to put on my pump performance curve chart. All right, my pump performance chart. So we would go just again, here's where we plot them out. And you remember like in it must have been 5th or 6th grade when you were doing charts and graphs in math class, and you had to do this kind of arithmetic to figure out how to put these different points on a chart. And you're sitting there thinking to yourself, this is crazy. I'm never going to use this in the real world. What a waste of my valuable 6th grade time. Well, today's the day. All right, today's the day this becomes important. Because what we've done here is we've laid out, without the pump curve, we've laid out the system curve with all these different points, and we simply connect the dots, and there's your system curve. All right, and your system curve exists in perpetuity for that system, because flow and head are directly related. Now all we do is we pick a circulator, put it on that system, and wherever the circulator's performance curve intersects that system curve, that's where the system's going to work. Now, what does that look like? Well, here we show a couple of Takeo 3-speed pumps, the 0015, which is your standard 3-speed circulator, the 0015, the Grundfos 1558, the B&G NRF 22, and all the others have basically identical pump performance curves, lower flow, higher head, steeper curves. We also have a 0010 3-speed, which is a replacement pump for old B&G 100s and Takeo 110 big 3-piece circulators, and with performance curves that very closely emulate what those circulators could do. So we have both of them on here, and what we're going to do is lay this out. Now again, for that zone that we figured out, 3 gallons a minute at 5 feet ahead. So this is my requirement. This is my requirement, and let's lay out the other points on the chart. All right. So here are the other points on the curve, and we lay them out and just connect the dots, and we'll see where we would intersect different points on the curve. And what this is telling us is the best choices here would be, if I'm using a 0015, my best choice would be low speed. By far, my best choice would be low speed. If I was using a 0010, the low speed choice would be even better. Okay, because we're minimizing the amount of space between my requirement and the pump performance curve line. So either one of those would work well. This, however, is a problem with 3-speed circulators, because I'm looking at a circulator here. I got a circulator with 3 speeds. Anybody out there who's been in the field and have seen 3-speed circulators, what is the default setting on 3-speed circulators out there in the real world? All right, I'll wait for your answer. 2, 3, 4. What do you got? Where are 97.5% of the 3-speed circulators installed out there in the wild? At what speed are those things set at? I know, Rick, you know this, and I know, Dave, you know this.
No, they got it too. They're chiming in.
Yeah.
So, yeah.
They're almost always set to contractor no callback mode, which is, if you're a fan of the movie Spaceballs, it's ludicrous speed. Okay, it's that, because if a little is good, a lot is better, and if a lot is better, everything the thing can do has got to be the best, right? And we're talking about a good size zone here too. 30,000 BTUs is a big honking zone. All right, it's a big zone, and it was 163 feet long. That's a long zone. So it's easy to intuit that, hey, maybe I need the high speed because it's a long, long way. But here's the thing. If I were to set it at high speed, dig what I'm doing here. I need 3 gallons a minute at 5 foot ahead under design conditions for this zone. What am I giving it? I'm giving it 5 gallons a minute at 14 feet ahead. All right. That's 2.5 times more flow than I need. All right. That's 2.5 times more flow than I need. So my delta T in this case, the best case delta T I'm ever going to see in this example is probably going to be about 12 degrees. And that's going to be on the coldest day of the year, the so quote unquote design conditions. So it's going to be 12 degrees, best case scenario. Most of the heating season, because again, I don't always need 30,000 BTUs. Most of the heating season, I'm going to need considerably less. Most of the heating season, gang, you're going to have a delta T that's going to be less than 5 degrees, less than 5 degrees. And that thing's going to short cycle like crazy. All right. But
For
no one's
shame.
going to be cold. Nobody's going to be cold. Hey, you say, I put it at high speed. Nobody called me up to complain that they're freezing to death. It's got to be right. It's got to be okay. Good enough. The price you pay for convenience here, the price you pay for you're not having to do the math, just set it to high and get the hell out of there. The price you pay is this right here. All right. Short cycling. You got components that are going to break down prematurely. And sometimes, people don't connect the dots, pardon the pun, don't connect the dots and say, hey, the reason all this stuff is failing, it's because they use crappy components nowadays. I'll never use that boiler again. That thing's a piece of junk, or these things stink. They're no good. They just don't last. No, they were short cycled into an early grave, is really what happened. They were
Yeah.
short cycled into an early grave. And this is more common than any of us really realize. One of the most chronic issues we have in hydronics today, in residential hydronics. All right, how are we doing out there, guys? Questions?
Yeah, they just commented based on your last question was what speed do they come? Another thing to remember, a lot of times us manufacturers will send it to you in the highest speed because we want
Right.
that thing to burp and that, we want to get the air out of it quicker. So again, a lot of times the factory setting or what it comes out of the box in is not necessarily the mode or the speed you want to leave it in.
Yeah, exactly. Yeah. That's why once you take it out of the box, you're in charge of that pump. All right.
That's right.
You are in charge of that pump and you are the master of your domain. You can tell that pump to do what you need it to do and what you want it to do. So again, a little bit of math goes a long way here in terms of making sure the system works to its maximum capabilities. I mean, we talk to folks all the time who say, well, I pride myself on putting in the best equipment, the most efficient systems, and everything's straight plumb, and it looks fantastic, it looks gorgeous, and my systems are the best. And they're putting these, and everything is true up until it comes to the point of choosing the circulator. Well, I use this circulator all the time because I get it for the best price and it's never failed me, and they always set them to high. So it's like it's doing like you're getting like 90% of the way there, and that last 10%, which is the most important 10%, we're basically not paying attention to. The circulator, as we said before, has more to say about the overall efficiency of the system and the long-term viability and performance of the system than we ever really gave it credit for. And for that, we thank ECM Circulators. So let's talk about sizing for variable speed circulators. Again, a lot of people still think, well, they're variable speed, right? You stick it in and it figures it out for you. It sizes itself. It finds its own place, that sort of thing, which is a great story, fundamentally untrue across the board, every manufacturer, but does make for a nice story. And I've heard people, I've heard, high profile people in this business say, oh yeah, this thing, you're going to love it. It's magic. It does the thinking for you. It takes the thinking out of it. And none of that is true. None of that is true. The machines haven't taken over yet. These things are not the Terminator, okay? You're still in charge. Like I said, you're still the master of your domain. You're in charge of what that circulator does. And we're going to go over that now. When we talk about variable speed circulators, nothing really changes. There's no magic involved here. No, none, zero, nada. There's no magic involved with variable speed circulators. It's still system curves and control curves. All right, control curves. Because this circulator is controlled by a little bit of a brain, okay, by some microchips. You get to determine its performance level. You get to determine how it operates and where it operates. All right. And understanding how and why that works is going to help you get the most out of the system. So it's still system curves and control curves, and those points of intersection, they still apply with variable speed circulators. Let's take a look at the Takeo 0015E3. It's a delta P variable speed circulator, meaning it changes its speed based upon changing pressure differentials within a system, all right? It reacts to changing pressure differentials, and its goal when set to either the low or the medium setting is to maintain a constant pressure differential within the system. What we're talking about is the ultimate flat curve circulator. Flow can change all at once, but the head pressure differential created by the circulator stays the same. It stays flat on that curve. Now with the 0015E3, we have 3 settings. For people who love 3-speed pumps but would really like 3-speed pumps to work better, the 0015E3 is kind of the answer to that question. At low setting, it's a constant 5-foot ahead pressure differential pump. Whatever the flow rate is whatever the flow rate is, but 5-foot ahead is constant, okay? Medium setting, we double it up. It's 10-foot ahead, all right? This medium setting, this 10-foot head setting, is also the permanent fixed setting for the 007E ECM variable speed circulator, all right? But the 15E3 has 2 additional settings. We have the low setting, and then we also have the high setting. Now with the high setting, it's a full speed, fixed speed, 44-watt pump, all right? 44-watt pump. A typical 007 or a 0015 standard efficiency might be upwards of 80 to 85 watts. This maxes out at 44 watts, but it's full speed, fixed speed, and it'll work on this pump curve just like a regular circulator does, all right? It's a full speed, fixed speed. Now, we wanted our 3 gallons per minute at 5-foot ahead for this zone. A lot of people say it doesn't make sense to use a variable speed circulator if it's a zone pump, because remember we said earlier, a delta P pump will change its speed based on changing pressure differentials it experiences in the system. Well, what changes? In a hydronic system, what changes pressure differentials? Well, zone valves opening and closing will change the pressure differential, right? A delta P pump will go faster when zone valves open, and it'll go slower when zone valves close. As a zone pump, nothing's changing, right? You don't run into any changes in pressure differential in a single zone. So it's never going to change its speed. A delta P pump will never change its speed when used as a zone pump, but that doesn't mean you shouldn't use it, all right? It simply means it's going to be a fixed speed pump, but we have the ability to fine tune as best we can where that pump's going to work. So in this case, at 3 gallons a minute at 5-foot ahead, I know it's 5-foot ahead. I'll set that sucker right to low. Under design conditions, 3 gallons a minute, 5-foot ahead, that's about as good as it gets. Now let's just put the rest of the plot points on that system curve out here, okay? And see what happens if we say, well, you know what, I don't know if I don't know what the actual head and flow is, or I didn't do the math, so I'm gonna guess, okay? Well, let's say I set it to medium, all right? I set it to medium. So instead of getting 3 gallons a minute, looks like I'm gonna get just over 4 gallons a minute. Okay, that's 1/3 more flow than I need. I'm gonna have about a 25% lower delta T under design conditions than is optimum, than is that 20-degree delta T. So I'd probably get about a 15, I'd probably have about a 15-degree delta T at best, Better than what we had before, but not ideal, obviously. And if you say, hey, I don't know what's going on, I'm just gonna set this thing to high and get the hell out of here. Well, I'm no better off in terms of my delta T than I was with the 0015 or the 1558 or whatever set to high. I'm no better off, other than I'm using about half the electricity, all right? My delta T is gonna be 12 degrees or less at best, and most of the heating season, it's gonna be less than 5. That's just the way it is. There's nothing magic here. It's not gonna automatically know it has to do anything. It's gonna work where the system curve intersects the pump performance curve, okay? That's just how they work. If I, and here's a look at that. So here's my 5-foot ahead constant pressure line. And the way a delta P pump works is it has a whole bunch of different pump performance curves that have been programmed in. All of these little curves you see in there are programmed in, and we based on where the system curve intersects, that's going to determine what performance curve it works on. So again, here's our system curve, like so, intersects 5 foot ahead right here. In fact, what it's doing is it's going to be operating on this pump curve right here. Okay, so if this is 44 watts and this is 4 watts, this thing might be working at about 9 or 10 watts all heating season long. Now we got a little bit more of an electrical saving story to tell, and that circulator sized about as solidly as it can be sized for in fixed speed operation. Any questions out there, guys?
No, right now it's looking pretty quiet.
So I've either put everybody to sleep or they're just on the edge of their seats. Which one is it, gang?
I don't know. That's how I always feel.
Yeah,
Never any questions, So
there you go. There you
this
go.
means
All right.
you're nailing it all down, John. You got
That
it.
must be it. That must be it.
Yeah.
Okay. Well, let me ask you guys a question. Does this make sense to you? Is this something new? Is this how you understood variable speed pumps to work, or is this something new and different, a different way of looking at these things? That I'd be interested in hearing from you about.
Emil says great. Somebody says they're too busy taking notes.
Good
Making
man.
sense. It's all looking good.
All right. All
Previously
right. All
understood.
right.
Tim had that one nailed already.
Very good. Very
Yeah.
good. All right.
Walter says you're doing a good job. Makes sense. Perfect.
Thank you. Thank you, Walter. You're my favorite in the class so far.
Well, David said perfect. So
Oh, okay. Well, that's pretty good. There you go. Now, we also offer a delta T variable speed circulator, the VT2218. The reason we call it the 2218, maximum speed, 22 feet ahead, out to 18 gallons a minute. Hence the name 2218. Makes sense to me. It's a delta T circulator, which is different from a delta P circulator. Now, a delta P circulator will vary its speed based on changing pressure differentials. Okay, the impeller feels changing pressure differentials, and it'll speed up and slow down. The zone valve's open, there's less resistance against the impeller, so to speak. So that's a signal for the circulator to speed up. Zones close, there's more resistance against the impeller. That's a signal for the circulator to slow down. A delta T circulator is the same thing, only different, if you will. It comes with two sensors. One sensor goes on the supply pipe going out to the zone, and the other sensor is on the return pipe coming back from the zone. And all it's looking for is the temperature difference between the two. All right, it doesn't care what those temperatures are. It doesn't set the temperatures, so it doesn't fight with outdoor reset or any of that other stuff. It simply wants to know the difference between the two, and it's going to try to maintain a fixed temperature difference for as much of the heating season as it can. So we can set this thing up for a 20-degree delta T. We set it up for a 20-degree delta T. Now, presuming all of our math was dead on accurate with very little to no fudge factor, which is a bit of a stretch, but let's just presume that that's the case. We want 3 gallons a minute at 5 foot ahead, right? Now, this is I'm not going to say this is a self-sizing pump because that wouldn't be accurate, but it's as close as we have in the industry to a self-sizing pump, meaning it's going to try to maintain that 20-degree delta T no matter what time of year it is. So under design conditions, what it's going to do is the pump performance curve is going to drop to meet the needs of the system to deliver that 30,000 BTUs while overcoming 5 foot ahead. And it's going to figure that out simply by making that delta T fixed. Okay, because remember, we had all these different items in that math formula. We had GPM, okay? We had GPM, and we had BTUH, and we had delta T times 500. Well, we know 500 is fixed. If we fix the delta T at 20 with this circulator, we know the BTUH is going to change with the weather, all right, or with zones opening and closing in a zone valve system. BTU load is going to change with the weather, and it's going to change with the number of zones opening. If the delta T is fixed, well, then the GPM will have to move in lockstep with the BTUs. All right, so the flow rate's going to change based on the load in terms of BTUs because we have that delta T fixed. Now, what's going to happen here is as it gets warmer, this is a zone pump, remember, as it gets warmer, this is going to go down. If the delta T is fixed, well, the flow rate has to go down as well, doesn't it? As it gets warmer out, the pump is going to go slower and slower until we hit line A, which is our minimum speed. Then it can't go any slower than that. At that point, we have a 9-watt fixed speed pump. So any warmer it gets, when it wants to operate down there, well, we're not going to have a 20-degree delta T. But the moral of the story is we're not going to have a 5-degree delta T either. All right, that's the advantage of a delta T pump. Ideally, a delta T pump is you get the most bang for your buck with a delta T pump if you're operating way up in here someplace. A little bit more flow, a little bit higher head, because that gives us a broader range of variable speededness than compared to, say, this as a zone pump, 3 gallons a minute at 7 feet ahead. If you have really small zones in a temperate climate, you may find that all you have is a 9-watt fixed speed circulator, all right? And a very expensive 9-watt fixed speed circulator at that. So the value may not be there, but the larger the zone, the larger the system, the more applicable a delta T pump becomes.
Hey, John.
Yes, sir.
One of the questions, Dave already answered it he typed it in, but because I'm guessing others are wondering the same. The VT2218, yes, you can adjust that delta T in from 5 to 50 in 1 degree increments. So you've got lots of adjustability. If for some reason you wanted a 15-degree delta T, you could dial that in there.
Right, exactly. Or if it was residential radiant, you wanted to be a 10, you could do that.
Yep.
For small snow melting applications, you could move it out to a 30-degree delta T. For an indirect, you could move it out to a 30-degree as well. Although with an indirect, you'd probably want a fixed speed pump, so you blast that thing and help it to recover as quickly as possible.
Typically.
Yeah, but again, yeah, you can adjust that from 5 to 50, and it's done very easily from the front control panel. Very good. Now, what about a zone valve system? All right, let's wrap this up and talk about a zone valve system. Now, in a zone valve system, I have one circulator and multiple zones. All right, so when zones open and close, a delta P pump or a delta T pump is going to speed up and slow down as zones open and close. Now, here's the funky thing about a zone valve system. A 3-zone valve system has 7 different system curves. It'll have 7 different system curves. It'll have one system curve for every possible combination of zones that could be open at any given point in time. Let's count them out. I've got 3 zones. So zone 1 by itself, zone 2 by itself, zone 3 by itself. There's 3 system curves right there. Then I've got zone 1 and 2, zones 1 and 3, zones 2 and 3, and zones 1, 2, and 3. That's 7 different system curves. So I'll have 7 different points of intersection across whatever control curve that I might be using. So that's basically what we're dealing with a zone valve system. Also with the zone valve system, if I have 3 zones and this is 3 foot ahead, this is 4 foot ahead, and this is 5 foot ahead, if I have to size my circulator, I'll size my circulator for the total flow rate. So I add the flow rates of zone 1, zone 2, and zone 3 together to get my 7 gallons per minute. But I don't have to add the head loss together because it's a parallel piping system. I only will base the pump size off of my worst case head loss zone, in this case 5 foot ahead. If I can overcome 5 foot ahead, I can sure as heck overcome 4 foot ahead and sure as heck overcome 3 foot ahead as well. So you don't have to add the head together. The flow you do, because that circulator at some point in time is going to have to deliver flow to all 3 zones. But head loss, if I can overcome 5, I can overcome 4, and I can overcome 3. So it's a good thing to remember because it keeps you from oversizing your zone valve pumps. So in this case, 7 gallons a minute at 5 foot ahead is what I'm looking at. So we go back to our 0015 E3. Looky, 7 gallons a minute, 5 foot ahead. I'm in great shape. All right. And if I were to plot out the rest of that system curve, it would be out here. So if I didn't know what I was doing and I wasn't sure, and I said, boy, I'll just set it to put it in the middle, set it to medium. Well, again, 7 gallons a minute at 5 is what I want under design conditions. What I'm really going to get is a little over 9, maybe about almost 9.5 gallons per minute at what looks to be about 8 foot ahead. Not horrible, but again, I'm over pumping. And my delta T is going to be smaller than it needs to be. All right. Here's the funny thing. If I set it to high with all zones calling, I'm going to be at exactly the same spot. The difference is going to be where the other system curves intersect along that line. So let's say here's all zones calling, and here's the system curve with one zone calling. all right, with my smallest zone calling. If I set it to low, all right, as zones close, all right, here's my different system curves. You can see what happens. I've got my different points of intersection. So a zone closes, bang, we go down here. A zone closes, bang, we go here. We go here, we go here, and we go here. We work
John,
across that line.
don't say bang.
Don't, I'm sorry, boom.
Okay, that's good.
How about we just quietly slide over there?
There
Because
you
banging,
go. There's no banging with these
yeah, the
things.
banging would actually happen up here.
Yeah, there you go. Good
If
way to
we're
say
intersecting up here, that's where zone valves bang. When they're closing against such high head loss or high head pressure differential, if you've ever had zone valves banging, this is why. A lot of people say, hey, if you got banging zone valves, put in a variable speed pump. That'll fix it. Yes, if you program it properly, that will fix it. If you
10-4.
don't, it won't. All right. You're in charge of what happens. You're responsible for that pump the minute you take it out of the box. You're responsible for its operation. So this is stuff you need to know. Right? This is stuff you definitely need to know.
Good stuff.
So again, we'll work down along here. If you really want to see how that works in regards to performance curves, again, here's our delta P constant pressure mode, all zones calling. Okay, here's my performance curve, or here's my system curve, and I'm working on this performance curve here. And as zones close, we slide this way, we slide this way, and we slide this way. Okay, and with one zone calling, I'm working on this curve. With all zones calling, I'm working on this curve. And compare the overall wattage consumption to if I had chosen the 10-foot ahead constant pressure line and really didn't consider the math, I'd be working way up here and way up here. Not bad, but I'm over pumping, B, I'm using more electricity than I need to. So I'm really not taking full advantage of this really cool piece of technology.
True.
Delta T gets a little easier as well. 7 gallons a minute at 5 foot ahead. By golly, this is where it's going to work. All right, this is where it's going to work. And as zones close, the performance curve is going to shift to meet the requirements of the system. And that is unique among variable speed circulators. In this case, as zones close, the performance curve is going to drop and drop and drop and drop until we're down, maybe this is where my smallest zone is under design conditions. I'm going to work here. And as zones open, I'm going to work up here at a higher speed. Again, at some point, I'm going to have a fixed speed 9-watt pump, and my delta T won't be 20, but it's not going to be 5 either, or less than 5.
Yeah.
All righty. Real quick, I just want to share with you as we wrap up the Takeo 0018E. And this is a product in 2 weeks on Takeo Tuesday. In 2 weeks, we're going to really dive deeply into this because this is kind of very, very interesting technology. And when we talk about how, once you take that pump out of the box, man, it becomes yours, man. You take control of what that thing does. The 0018E with Bluetooth connectivity to the 0018E app gives you more control over a circulator than any circulator on the market. You can dial that circulator in about as well as a circulator can be dialed in. You have multiple operating modes. Okay, you have proportional pressure, you have constant pressure, and you have an infinitely variable fixed speed setting if you're using it as a zone pump. So you have different ways to program it without the app. But if you put it into the Bluetooth mode and connect it to your phone or to an iPad or whatever, any kind of a device, Android or iOS, you open up a whole new world of possibilities. So without the app, you have two, right here, you see them, you have two constant pressure settings, all right? When you connect it to the app, you have 9 different constant pressure settings, all right? And you have a multitude of different operating modes as well. So you've got a multifunction. What the 0018E is, it's a multifunction delta P pump, meaning it be proportional pressure for continuous circulation, thermostatic radiator valve type applications for a circulator that size. You have constant pressure, which is your zone valve setup, And then you have infinitely adjustable fixed speed, which you can use to your advantage in a zone pumping situation. All right, and we also have something called active adapt, which I'll explain real briefly in a second. But again, we got all these different options. What it does, and I'm going to credit Dave Holdorf for coming up with this analogy. What it does is it allows you to see inside the pipe. What's going on inside that system, and how can we fine tune this system to best meet its needs, okay? And again, here's your Bluetooth communication operating modes. In the blue mode, what you have here is an infinitely adjustable, an infinitely adjustable fixed speed. What you'll see is this blue range, the circulator can work anywhere within there along its, as long as we're working on a system curve. It'll tell you where the system curve is. You'll be able to plot along there. But this little slider here, this little dot up there is a slider. You put your finger on it and you can slide it up and down from 0% up to 100% and adjust the speed of the circulator. And what'll happen is, as you adjust the speed of the circulator, you will see in real time this dot move to a certain point to different points on the chart. And down below here, you'll actually see the GPM. So again, say you don't even, in this case, you don't even have to figure out the head loss. You just have to know the flow rate. So if you know it's 30,000 BTU zone, well, that's 3 gallons a minute. You simply move this dial until you see 3 gallons a minute here. This part will take care of itself. All right, that part will take care of itself. The head will take care of itself. In a zone valve system, we have 9 constant pressure curves, and you can change which curve the system is operating on simply by touching a different line. So here, way up here, we're way up at the top. Basically it's at curve number 8, and I want it to work down here at curve number 2. All I have to do is touch my screen right there, and bam, that circulator will recalibrate itself, and it'll operate now on this curve and basically ignore what's up there. So you have the ability to really fine tune that. We also have the proportional pressure curves, again, continuous circulation, thermostatic radiator valve applications for a pump this small, and then something called active adapt, which again, it's one of those, it's that thing that everybody thought was magic. Hey, you put it into active adapt, you put it into auto adapt, and the circulator will magically size itself, not even close to what either of them do, okay? And it has to be continuous circulation with modulating valves. Active adapt is more of an energy savings thing than a self-sizing thing. And again, in our next session in 2 weeks, we can actually dive a little bit more deeply into what that does, and more importantly, what that doesn't do. Okay, there's no such thing as a self-sizing pump. Maybe the closest thing we have is a Delta T pump, but that's about it. Alrighty, gang. How was it for you? I want to know that. Where are we at with questions, and what did you get out of this? Was this worth it to you? And I do thank you for your time. It's 1:03 here in the East Coast. Throw some last minute questions out there, and oh, here we go. We got one of my favorite ones about a pressure differential bypass valve. Pressure differential bypass valve is it's a band-aid for a self-inflicted wound. It's just it's what we've had to do. It's what we've had to do to compensate for using the wrong pump. All right. I guess I can't really say it any better than that.
Yeah, we use those to change that steep curve pump into a flat curve pump, so you don't get the noise going on.
Right.
Or the change from an AC circulator to an ECM circulator, so that is going to have that flat curve constant pressure mode in there. So Rick was also mentioning before, you don't want to use a pressure differential bypass valve with an ECM circulator because it will confuse it and just run full out and never modulate the flow that you got going on there. So that's it.
Right. Yeah, Dave said that a pressure differential bypass valve simply turns a steep curve pump into a flat curve pump, and in that case, why not just use a flat curve pump in the first place, right? There's really no need for that.
You service guys, if you run across one, you can still put an ECM in there. Just take the pressure differential bypass valve and completely close it. Typically it's righty tighty. Tighten the thing way down so it doesn't ever want to open up, and then then you can put the ECM in and it'll work like it's supposed to.
So we got a great comment that came in from Gene Bennett. Thank you.
I just
And he
saw
was
that.
saying, so we can get rid of balancing valves if the circulators are used, meaning sized properly. So yes, like the 18 that John was showing you right there at the very end, you can dial it in exactly to what you want it to do or what you need it to do, and you may be able to get rid of some balancing valves. So and I find a lot of times we don't see a lot of balancing valves in a residential setting or on the small side here. But when you get into the larger side, when you're looking at your triple duty valves and balancing the system flows out that way, correct. You can size these circulators now that they are variable speed to the design that you need rather than the oversized design and then twinning it, bringing it back to what you want it to do. Exactly.
I think I'll take a slightly different tack on that question about balance valves, and I'm going to think about radiant systems for a moment, where you
Yes.
have different loop lengths on a manifold. Well, this is a pressure regulated circulator, so I don't have to worry about balancing my loops. Oh no, you absolutely have to, because let's presume they're all open at the same time. The pump can only run one speed at a time, no matter how well you dial it in. It can only run one speed at a time. And if I've got short loops and long loops on one manifold and they're all open, and they're not balanced, where's the flow going to go? It's going to go to the short loop. That's just math. That's just reality. So you still have to, if you're on a radiant manifold, you still have to balance the different loop lengths and basically trick the water into thinking all the loops are the same length. But that's basically what you have to do there. It's not going to equalize those loop lengths, if that's kind of where we were going with it.
Right. Yeah.
It's a good question from Jim Macheko. I hope I pronounced your name right, Jim. When using a thermostatic radiator valve, what does the pump do when all the rads are shut off and the pump has no electrical feedback? It keeps running. It's going to run at a very, very, very low speed, but it does keep running. With pumps this small, and I'm glad you asked that, with pumps this small, deadheading for brief periods of time really it's not the same concern that you would have with a much larger pump, a 1 horsepower or above circulator. Yeah, you don't want to deadhead it, but these little fractional horsepower circulators, if you deadhead it for a few minutes or for a little bit, it's really not a big deal. And the thing about thermostatic radiator valves, just think of what has to happen for all of them to be closed at the same time for an extended period of time. Those things are always modulating. They're opening or closing at their own paces. So yeah, would you deadhead a pump? Yeah. Is it a concern? Not really. Not with a pump that small. Not really. Not really.
Yeah, whatever control platform you're using with a TRV style system, if it is going to turn, the control platform is going to turn the boiler on and off, then you wire the circulator to the boiler that way. So this way it's not running all summer like John was saying. So short periods of time during the heating season, not that big of a deal. But now all of a sudden when it becomes the summertime, why consume any electricity whatsoever? So you do want to make sure you turn it off. You just don't want to plug it in and just leave it alone because, hey, 5 watts is still 5 watts all summer. So
Right.
my suggestion is always have some sort of control to turn the circulator off. Short periods of time, not a big deal.
Right. And even systems that are running where the circulator is running all winter long and it's on a switch or on a set point or something like that, even if that circulator is running continuously, which if you're using a circulator that's electrically efficient so you don't use as much electricity and then you leave it on all the time, doesn't make a ton of sense to me, but hey, what do I know? Excuse me. If the circulator is running really, really, really low, again, even if it is running continuously and those TRVs are mostly closed, this is when you'd use proportional pressure. Yeah, it's going to go down. As Dave said, you're going to be at work. The thing's going to be rotating at about 5 watts, which isn't much at all. It's really not going to hurt the pump. We've learned that really does not affect the pump in any way. Big pump, 1 horsepower and above, yeah, you really don't want to deadhead it. Small pumps, it's okay. It's not, you don't want to go there. You don't intend to go there, but if it happens, it happens. And it's not the worst thing in the world.
So I had another question come in from Tim. Tim Pan, he was asking about, do we have any experience with loose metal in the system attracting to the ECM circulator, to the pump itself? So we will go into detail in 2 weeks on that as we do the deep dive and take the circulator apart. But we have a barrier to prevent any of those ferrites and particles in the water from getting to the magnetic part of the circulator itself to help protect it. If you have serious issues with water quality, then magnetic dirt separation is probably something that you want to do, which we will also be covering off in another Takeo Tuesday class later this season.
Very good. I see Jim's asked a bunch of follow-up questions. I want to make sure, did we answer your question, or are we making you did we give you the right answer, or did we give you the answer that you're looking for, Jim? Just let us know. I want to make sure we're in the right spot here. All right. Well, Jim, if you chime in, let us know. Thank you, Jerry. Appreciate it. Glad you enjoyed it. And again, as you guys will see in the coming, probably by this time tomorrow, you will get an email from us with a link to the recording, as well as a link to download a certificate of attendance. So that'll be there for you. And again, you can go back and watch this thing as many times as you like, and share that with people if you want to as well. Hey, the more the better, right? But with that, if there aren't any more questions, I'd like to say thank you. I really appreciate the gift of your time, folks. It's always fun to spend an hour with you a couple times a month. And again, in 2 weeks, we will be doing a deep dive into the Takeo 0018, and we'll be talking about the different operating modes, and we'll give you a bit more of a lowdown on that active adapt and what it does, what it doesn't do, and when you might consider using it in a residential application. In a circulator as small as the 0018, they're very limited. We have larger pumps, the 0026E and 0034E, that have that operating mode. And for larger pumps like that, you will see more opportunities to use it. But for a pump the size of the 0018, they're very few and far between in this country, or in North America anyway. So cool, folks. Appreciate the gift of your time. Have yourselves a fantastic Tuesday, and we will see you down the road a spell. Any final words, gents?
Nope.
Yeah, when we get into 2 weeks from now, I've got a working display, so we're going to see live time operation of the 18 and what we can also see out of, say, the 15 and the 7 also at the same time in that smaller circulator world, with and without zone valves. So it's going to be a good class, and we'll also go into how they're built and what's put together inside of them. So but look forward to seeing you all. Greatly appreciate you guys all stopping by. Greatly appreciate it.
All righty. Thank you all. Have yourselves a fantastic rest of the day and rest of the week. Take care, everybody.
Enjoy.